All right, everybody, we're going to talk about partial fractions here. But before we can talk about partial fractions, of which an example is the yellow problem on the screen here, we need to talk about adding and subtracting rational expressions. So remember, when you add fractions, they need to have a common denominator. And when you have rational expressions, which are fractions that have variables in the denominator, we often have to work to find the common denominator before we can start working. So in order to find a common denominator, we would take the denominators of my fractions, x plus 2, and factor them, and x plus 1. And then x squared minus 1 is x plus 1 and x minus 1. And then we need to make sure that both the denominators have the same factors. So you notice how we have an x plus 2 and an x plus 1 in the first denominator, and an x plus 1 and an x minus 1 in the second. Well, in the first denominator, we're missing the x minus 1 that we had in the second denominator. So we need to put that in to make the denominators common, but when we do, we also have to multiply the numerator by that. In the second denominator, we are missing an x plus 2, so I need to put x plus 2 in the bottom. Do the same thing to the top to keep the fraction equivalent. Now, my common denominator is x minus 1 times x plus 2 times x plus 1, and you can multiply that if you want to, not a big deal right now. And then this numerator would have been 3 times x minus 1, which is 3x minus 3, and then this one gets added, x squared plus 2x, and then I combine like terms. Now, this is something that you learned in Algebra 2, and you probably did in last year in geometry. Sorry, not geometry, pre-cal. I'm going to be lazy and write LCD here. Now, what I want you to notice is the denominator that's here were made up of factors that were found in the original numerator. Now, the process of decomposing into partial fractions is essentially the reverse of this process that we just did. Instead of starting with two fractions that we want to add and getting the sum, combining them into one, we are starting with the sum after they've been combined and trying to break them into the original fractions. Now, there's a simple process to this, and so I'm going to walk you through it. And these are, by the way, the PF problems from your summer packet, the very last set of problems. And this is PF1c. All right, so whenever I am trying to break up a partial fraction decomposition, the first thing I need to do is to look at the denominator and make sure it's factored. Well, in this problem, it is, but if you look at PF1b, it's not. So we need to start by factoring that denominator. Then once you factor it, in this class, all the factors are going to be what are called unique linear factors, meaning you're not going to have repeated factors. So you have an x minus 1, an x plus 2, an x minus 3. You wouldn't have two x minus 1s in this denominator. And they're all going to be linear, so you won't have any quadratics that wouldn't factor down any further. So when the factors in your denominator are all unique linear factors, what you do is you essentially say, okay, for each of those factors, I could have had, a denominator that had that factor in it. So that x minus 1 could come from a fraction that had x minus 1. The x plus 2, same thing. The x minus 3, same thing. Now, this gives us three fractions, right? So what I'm going to do is I'm going to say, I want to know what these sums are. That would, when I add it together, gives me x squared plus 2 on top. And the way we do this is, since each of these things in my denominator is linear, the thing we're going to put on top of the fraction is unknown, so we're going to represent it with a letter. But it's also going to be 1 degree lower than my denominator. And there's many reasons for that, which we can go into at some other point, to sort of get you through the process here. So which means, if these are linear, we need to have an x to the first as their biggest thing. On top, there's going to be basically just a number. So in this first fraction, we'll call that a. Second fraction could be a different number, so we'll call that b, and then c. So what we're trying to do here is to find a, b, and c. Now, the first thing we're going to do is we're going to treat this equation as if it's true, meaning we're going to do something to both sides of the equation, and that'll keep it balanced. And what we're going to do is we're going to multiply through by the least common denominator. common denominator we started with, which is this x minus 1, x plus 2, x minus 3. When I do that on the left-hand side, I'll be left with x squared plus 2. When I do this on the right-hand side, the first fraction, the x minus 1, would cancel. And that would leave me with a, the x plus 2, and the x minus 3. From the second fraction, the x plus 2 would cancel. Leaves me with b, x minus 1, x minus 3. From the third fraction, c, x minus 1, and I'm running out of room, x plus 2. Now, our goal here is to figure out what a, b, and c are. Now, there is a strict, sort of very algebraic way of doing this, and there's sort of a fast and dirty method to find this. We are totally, and you won't hear me say this often, we're totally going to use the fast and dirty method, and it's fine. So the fast and dirty method sort of works like this. We want this to be true. Whatever we find for a, b, and c, we want it to be true for all x's. So what we're going to do is we're going to pick convenient values of x that will let us find a, b, and c. Now, what that means is this. If I look at this first term, we've got a, x plus 2, and x minus 3. If I let x be negative 2, then that term, the one with the a in it, would go away, right? And also, the term with a c in it would go away. And what would be left is this side and something that only has b in it. So I'm going to think of plugging in numbers for x that make factors equal to 0. So what this looks like here, on the left-hand side, I had an x squared plus 2. So this is going to be negative 2 squared plus 2 equals b times negative 2 minus 1, negative 2 minus 3. And so what I get is 6 equals, and that's negative 3 times negative 5, so 15b. And that tells me that b is 6 over 15, which is 2/5. To find the others, you would do the same thing. Now, I look at the b, and I say, okay, I could let x equal 1 or x equal 3. So I'm going to let x equal 1. When x equals 1, this would go away, and this would go away. And so what I'd be left with is the left-hand side, x squared plus 2, and the right-hand side, a times 1 plus 2 times 1 minus 3. If I simplify that, I get 3 equals, that's 3 times negative 2, so negative 6a. So a is negative 1/2. And we're going to do the same thing by looking at the c term. Now notice, we've already let x equal 1, and we let x equal negative 2, and that found us a and b, right? So what we need is a number that will make a and b go away, and if you see, they share the x minus 3 factor. So I'm going to let x equal 3. When x is 3, that's going to go away, and that's going to go away. So what I'm left with is the left-hand side and the c stuff. So what I get is 11 equals, that's 2 times 5, so 10c. So c is 11/10. So once you've found the a, b, and c, you have now found the numerators, of each of the fractions that I started with, these 3. So essentially, my a was negative 1/2. So I could write that as negative 1/2 over x minus 1, or I could write that as negative 1 over 2 times x minus 1. b was 2/5, so I could write that as 2 over 5 times x plus 2, or 2/5 over x plus 2, that would work as well. And then my c was 11/10, so that would be 11 over 10 times x minus 3. This is the partial fraction decomposition of this fraction. And what that means is, if I were to go through and find the common denominators here and add them all together, what I would get is this sum. So I'll leave you to do a and b now, which are easier problems than this one.